Hello friends, welcome to the channel. So last class we discussed about Kohlrausch law and its applications, right? Today we are going to study about few more terminologies in electrochemistry and their related formulae. So yeah, come on, let's get started. So today first we are going to discuss about diffusion and its relation with ionic mobility. So diffusion. So we all know what is diffusion, right? Diffusion is the movement of particles from a region of higher concentration to a region of lower concentration, right? So movement of particles from higher concentration to lower concentration, right? This is called as diffusion. So in solution, any one of the component, it's migrated from a region of higher concentration to a region of lower concentration. This is called as diffusion. So each ion in solution possesses a coefficient called diffusion coefficient, which is given by the letter D. So D here stands for diffusion coefficient. So what is the purpose of diffusion coefficient? It is a factor which measures the mobility of ion. Okay, so it measures the mobility of ion. Okay, so we already studied a term called ionic mobility. So ionic mobility also measures the mobility of the ion, but that is due to kinetic energy and this is due to thermal energy. Okay, so the relationship between diffusion coefficient and ionic mobility is given by D is equal to U kT by E Z, right? Where D is called the diffusion coefficient, U the ionic mobility, K the Boltzmann constant, T the temperature in Kelvin, E the electronic charge, and Z the charge number of the ion. Okay, the term K and T altogether is called as thermal energy. Okay, thermal energy, right? So diffusion coefficient gives the mobility, is a measure of mobility of ion with respect to thermal energy. Okay, next we'll see the relationship between molar ionic conductance and mobility. So molar ionic conductance is given by lambda plus or minus at infinite dilution and ionic mobility at infinite dilution. So we are going to see the relationship between molar ionic conductance at infinite dilution and ionic mobility at infinite dilution. So in earlier videos we saw that as mobility increases, molar conductance also increases, right? So the relationship is given by the formula lambda plus or minus naught is equal to Z U plus or minus naught F. Here lambda plus or minus naught stands for molar ionic conductance at infinite dilution, Z is the charge number of the ion, U plus or minus naught is the ionic mobility of the ion at infinite dilution, and F is the Faraday. So Faraday is given by the value 96,500 coulombs. Okay, this is a relationship between molar ionic conductance and ionic mobility. Okay, now we are going to see the relationship between molar ionic conductance and viscosity. Okay, now suppose an ion moves through a liquid which is highly viscous. Okay, so what happens? The mobility of the ion is retarded. Why? Because due to the frictional force acting on it. So if a liquid is more viscous, then there is high viscous frictional force, right? So it's given by a formula called Stokes law, right? Stokes law, where it is given F is equal to 6 pi eta Rp, right? Where F is the frictional force, eta is coefficient of viscosity, right? So we see here that F and eta are directly proportional, right? F is directly proportional to eta, right? If you remove the constant terms, we can see F is directly proportional to eta. That is, as viscosity increases, we see the frictional force acting on the ion also increases. So the frictional force retards or resists the movement of the ion. Hence, on increase in viscosity, the mobility of the ion decreases, and hence molar ionic conductance also decreases. Okay. Now consider any ion, especially larger ion like trimethyl ammonium ion. Okay, tetramethyl ammonium ion, and we take the molar ionic conductance reading, okay, in different solvents. Okay, now you take the ion tetramethyl ammonium ion and you measure the ionic conductance value by experimenting it in different solvent. Okay, different solvents means those solvents having different coefficient of viscosity. Okay, then we find that the delta, the product of molar ionic conductance and the viscosity coefficient of the medium or the solvent is constant. Okay. Okay, so you took this ion and you did and you measured the molar ionic conductance, that is this value, at different solvents having different eta naught values. And when you took the values and you multiplied it, you find that all the values are constant. So this law is called as Waldens rule. Okay, Waldens law or Waldens rule. Okay, he said that when you take a particular ion and you measure the lambda naught values at different solvents having different coefficient of velocity, the product is found to be constant. It is called as Waldens rule, and this Waldens rule is obeyed only by large ion like tetramethyl ammonium ion or picrate ion. Okay, picrate ion. So this law is obeyed by only larger ions. Okay, so suppose a solvent has high viscosity coefficient. So we said that when viscosity increases, the mobility decreases, and hence the molar conductance also decreases. So for a solution which has higher viscosity, gradually this decreases. So when you see eta increases, this decreases. So if suppose a solution has the value of viscosity very low, then this will be high. So it is very inverse. So the value always remains a constant. Okay. So now a question arises: why only large ions obey this law and smaller ions do not? Okay. So we already said smaller ions are solvated highly, right? So smaller ions are solvated highly when compared to the larger ions. So the degree of solution varies with different solvents, right? So hence the smaller ions do not obey the Waldens law. Experimentally different values are obtained. So hence only larger ions, because do not get much solvated when compared to smaller ions, right? So larger ions obeys Waldens law, but smaller ions do not. Okay. So now let's see the effect of temperature on molar ionic conductance. So we know that as temperature increases, right, viscosity decreases. So on increasing temperature, viscosity decreases. So if viscosity decreases, naturally molar ionic conductance increases, because as viscosity decreases, frictional force exerting by the liquid on the ions also decreases, and hence mobility increases, which in turn increases the molar ionic conductance. So naturally when temperature increases, molar ionic conductance also increases.